In this next video, we're going to be looking at a few different topics, and they're all very important. If anything in these videos is unclear, please do contact me and ask questions, because I want to make sure that you understand this material, and I'll get with you and we'll go back and forth until everything's solid. But without any further ado, let's go on to the next slide. Next, we want to look at something called conservation of momentum. This is a fundamental rule of nature, and it's very, very important. It's a very, very powerful tool for physicists to be able to understand the universe that we live in. We know without a doubt that momentum is always conserved under the right conditions. Now, we're going to talk about what it means for momentum to be conserved, and also we're going to talk about what the right conditions are. So let me just give you the definition. What does it mean, conservation of momentum? And basically, the law of conservation of momentum tells us that in the absence of an external force, the momentum of a system remains unchanged. Now, the momentum can move from one part of the system to another part of the system, but the total momentum has to be the same. That's why we say conserved, not constant. The total is constant, but it can transfer from one part of the system to another part of the system, and so we say conserved, and that's the distinction. Now, here we have a figure of a cue ball striking an 8-ball, and momentum is conserved if you pick the right system. And so let's think about what's happening here. If you've ever seen someone play billiards, you might have seen the shot where the cue ball comes in, it strikes the ball, the cue ball comes to a dead stop, and then the other ball goes on. So we can think about that as, sort of an idea of what might be happening here. And so we get to pick what we consider our system. We could consider just the 8-ball as the system, the 8-ball by itself, just the cue ball as the system, or we can consider the system as both balls together. So let's consider just the 8-ball as a system. So let's see what happens. So initially the 8-ball's at rest, and then afterwards it's moving. So is its momentum the same before as after the collision? Obviously not. It's got zero momentum before the collision, but it's got some m times v after the collision. So its momentum has changed. In this system, the momentum is not conserved. Now, what about the next system, the cue ball system, where we're considering just the cue ball? Initially, it has some momentum, but then it strikes the 8-ball. The 8-ball goes on, but the cue ball stops dead in its tracks. So is its momentum conserved? The answer is no, because initially it had some momentum, but afterwards it had no momentum. So the momentum has changed. In other words, the 8-ball has applied an impulse to the cue ball and changed its momentum. So the momentum is not conserved because the momentum has changed. Now, let's look at the third and final system, both balls together. Here, the momentum of the cue ball is not zero, and the momentum of the 8-ball is zero. They collide, and then it's reversed. The momentum of the cue ball turns into zero, it stops, but the 8-ball goes on, and it steals the momentum of the cue ball. In this system, the momentum is conserved because it's transferred from one part of the system, the cue ball, to the other part of the system, the 8-ball. And in that case, when the system is like that, we would say that the forces here are internal forces. They're inside the system. That means they act like Newton's third law forces. Remember, we talked about the horse, and we could talk about, the horse and the cart, and so there was the force on the horse and the force on the cart. This is the same kind of thing. But if we choose both of them together, the forces are internal forces, and they do cancel out. Internal forces cancel, external forces don't. That's really subtle, so I hope that that's clear, that when we're picking just one ball or the other, the force is acting as an external force because there's only one. But when we consider both balls together, the two forces are a Newton's third law force pair, and they cancel each other out. The next example is another application of the idea of conservation of momentum. Imagine firing a rifle or firing a cannonball out of a cannon. It's the same principle. And so here I have the cannon, and inside the cannon is the cannonball, and it's before we have lit the cannon, so the cannonball has not been fired. The total momentum of the system, cannon plus ball, is equal to 0 because both of them are at rest. Now, I ignite the gunpowder explodes, expanding gases push the ball down the barrel of the cannon, and the ball shoots out of the cannon. It now has a positive momentum, a momentum that's going that way. But what was the initial momentum? The initial momentum was 0 for both things. So since this is another example of an internal force, because we're considering both the ball and the cannon together as our system, what must happen to the cannon? It must have a momentum in the opposite direction to keep the total momentum 0, because it was 0 when we start. The total momentum must maintain 0 after we have the explosion of the cannonball being launched. And so what that means is that the cannon must have a backwards velocity. It recoils. If you fire a rifle, it's the same way. That's why if you fire a rifle, you want to brace the rifle against your shoulder so that that rifle doesn't kick back and strike your shoulder and injure you. Now, one thing to note, the cannonball, it can be pretty massive, but it's way smaller than the cannon itself. And so here we have a situation where you've got a little mass and a big V going this way, but the cannon is going to have a big mass and a little V in the opposite direction. And so the cannon doesn't move nearly as fast as the cannonball, but it does move backwards because of that recoil. Now we're going to switch up and we're going to look at a completely new concept. So we're done with momentum and impulse. This is a brand new idea, and it's the concept called work. Now work is defined as force times distance, and specifically it's the parallel part of the force times the distance. Now what does that mean? It means the part of the force parallel to the motion. So I found a picture of a guy pushing a lawnmower, and he's pushing the lawnmower at a downward angle. And so that downward angle is something like this. Well, part of that force is going down into the ground. And so he's actually pushing the lawnmower into the ground a little bit. But another part of that force is parallel to the ground, along the motion. And so of these forces, only the part that's along the motion does work. So how could you figure that out? Well, actually, there's a whole branch of mathematics called trigonometry, which is all about doing that, but that's a little bit beyond the scope of this course. So I would have to give you a problem where I said, something like this was 40 newtons and this was 30 newtons and this guy was 50 newtons, and I could say how much work is done if this guy goes 10 meters. Well, the work is going to be F parallel times the distance, which is 30 newtons times 10 meters, and that would be 300 newtons times meters, and that would be the work of that force. So only the parallel part does work. And so we saw in the last slide our definition of work, the parallel part of the force times the distance. Now, I just want to point out that if the motion is in a line and the force is also in that same direction, then all of the force is parallel, and in that case the work is just the whole force times the distance. But if the force is at an angle, you would only take the parallel part of the force when calculating the work. Now, as we saw previously, the units of work are force units, which is newtons, times the distant units, which is meters. But there's actually another word that represents the units for work and also for energy, which is something we're going to talk about later. both work and energy have the units of joules. And 1 joule is equal to 1 Newton times meter. That is the relationship. Now, we also have one more very important idea, and it's this. If the force is opposite to the direction of motion, in other words, if something is moving this way, and maybe there's like friction, which is in the opposite direction, the direction of the force is opposite the direction of the distance, then the work is negative. And then also, you can see kind of over here on the right, I've got this figure here. If there's no motion, there's no work. And so imagine, you can see the picture of this guy, he's pushing against the wall, but the wall's not moving. There's no distance that the wall has moved. So even though he's pushing, there's no work done. There has to be a displacement, a motion, in order for there to be work. So, he's pushing against the wall, his muscles are vibrating, they're getting tired. Where's the energy that he's exerting to his muscles going? Well, it's going to thermal energy. His muscles are warming up. And so rather than doing work to move the wall, he's doing work inside his own body. Now we've talked about work, and the next thing we want to talk about is energy. And energy is defined as the ability to do work. That's it. That is energy, the ability to do work. Now it turns out there are many different kinds of energy. And one kind of energy is called potential energy. Potential energy is the energy that a body has due to its position. And so that is the official definition. Now, very often people are taught that potential energy is stored energy. That's actually not the best definition, but it can be a very useful way to think about what potential energy is. And we can think of energy as stored. And so imagine I have a spring here, and I compress the spring. You can see here the hands are compressing the spring, or alternatively, I could grab the spring and stretch the spring. In both of those cases, I've changed the position of the spring. I've stretched it out or pushed it closer together. And by doing so, I load it with what we call potential energy. So that when I release my hands, here the spring's going to expand back out. Here the spring is going to contract back to where it was before. And so by stretching or compressing and changing its positions, I load it with kind of a stored energy so that when I let it go, it gets restored back to where it was. Another kind of potential energy is the potential energy associated with gravity. So you can see I've got a picture of a girl here that's got a ball. She's holding it over this cliff. If you had the ball down here and you lifted it up here, what you've done is you've changed the position of the ball, and by doing so, you've loaded it with this potential energy so that if she lets go of the ball, what happens? It falls back down to where it was. And so that potential energy can get converted into motion, and that is the basic idea. Now, there are many kinds of different potential energies. There's potential energy of a spring, there's potential energy due to gravity, there's potential energy due to electrical forces, there's many other kinds of potential energy. In this class, we're really going to just look at gravity as sort of our model for how potential energy behaves. So we're going to really only concern ourselves with gravity. And the way that you calculate the potential energy for gravity is simply through the formula mgh. And so the idea here is I've got some mass, this ball, and I lift it up some height h. And so m times g times the height h, that is our potential energy. Now, what's interesting, if I lift this guy straight up, I've lifted it straight up 3 meters. if I push it along this hill, I may have pushed it 5 meters, which is longer than 3 meters, of course, but the height change is only 3 meters. And here I can, drag it up these steps, and so it goes much longer distance than 3 meters, but again, the height change is only 3 meters. So in each of these three cases, they have the same potential energy, mgh. And just FYI, I'll remind you that the weight of something is equal to m times g, where little g is at 10 meters per second squared. That's the acceleration due to gravity. And of course, m is the mass. And if you're talking about potential energy, we've got the weight, mg, times the height, which is represented by h. And so height. And so that is the height. And of course, this W stood for the weight. Okay, so here's an example that we can look at. A 90-kilogram person climbs up several flights of stairs to reach a height of 120 meters. What is their change in potential energy? And so, well, let's think about that for just a second. We can say that the change in potential energy is going to be the final potential energy minus the initial potential energy. But what's the initial potential energy? The potential energy initially, mg, what's the height at the bottom? 0. And so that equals to 0 joules. So the final potential energy is just mgh, and we can plug that into our formula here. We can say the mass is 90 kilograms, little g is 10 meters per second squared, and we know it's really 9.8, but we'll use 10 just to make our lives easier. And then the height change is 120 meters, and so the final potential energy is 10,800 joules. And so that minus 0 gives you the change, and the change works out to be about 11,000 joules. That is the change in potential energy. And if we need to be specific, we can say it's 10,800. Here's another example. An object that weighs 50 newtons is lowered 10 meters. What is its change in potential energy? I want you to stop the video and see if you can figure that out. No, really, pause the video, see if you can work it out. Did you do it? I'm guessing that most of you probably didn't do that, but I really hope that you will. I really hope that you'll stop the video and give the example a try, because that's how you learn. If you don't do that, if you're not willing to, struggle with some of these problems, you're not really going to learn it as well as you would otherwise. So I hope that you'll take my advice and do that. Pause the video, work through the problem if you can, and if you get stuck, that's okay. Come back. I'm about to show you how to do it. Okay? 3, 2, 1, pause. Okay, we're back. So let's look at that. So again, there's two things that are tricky about this example. One, instead of giving you the mass, they give you the weight. And so that's equal to the whole mg. And so we know that that part is the weight, and then times the h gives me the 50 newtons. And so the other thing that's tricky about this problem is the fact that it's lowered. We know that usually things that are going down, we call them negative. And so if I say this is a height equal to 0, if I lower it, my height is going to be negative 10 meters. And so my potential energy, this is my initial potential energy, that's going to be mg times 0. My final potential energy is going to be mgh, which is mg times negative 10 meters. That's equal to 50 newtons, that's our whole mg, times negative 10 meters. And so our final potential energy is equal to negative 500 joules. and then the change in potential energy is the final minus the initial, which is minus 500 joules, minus the initial, which is 0 joules, and that whole thing works out to be minus 500 joules. That's a J for joules, and that works out to be our complete answer, minus 500 joules.